So we arrive at section 4.6, which is the change of state. Now, this section has various different types of questions. I think that's what makes it difficult for some people. And for everyone, they'll have to think critically. Everyone has to think critically about this section. But the fundamental principle behind this is super intuitive. Okay, when it comes to change of state, what becomes unintuitive is one little fact, but I think you'll find it cool. So first of all, change of state between solid, liquid, and gas. Well, here's an example of it. Here you have ice, and you can see the packing of particles. Then you have water. You can see the unpacking of particles, more spread out. Here's the crazy thing. Look at the temperature. Have you ever thought about the melting point of water? You know, sometimes you're like, what is it? Melting, freezing. Temperature is at 0, yet it's phase changing. What's going on there? This is called latent heat of fusion. This is a critical point. Okay? 0 degrees Celsius for the substance of water is a phase changing point. Okay? If you are taking away energy, it will become ice, and if you're adding energy, it'll become water. In this case, let's suppose we're adding energy. So let's suppose you have ice, and ice is at 0 degrees Celsius. If you continue to add energy, it will phase change to water. However, the temperature will not change during that transition. That is the unintuitive part of this. Okay. So, what does this mean? What does exactly this mean? The specific latent heat of fusion is the quantity of heat needed to melt 1 kilogram of a solid without change of temperature. Okay, so actually, and I'll just present the next point as well before. Okay, the specific latent heat of vaporization would be the quantity of heat needed to vaporize 1 kilogram of a liquid without change of temperature. So again, we have water going to steam, yet it's maintaining its temperature. So what the heck is going on here? Well, basically, let me draw you a picture. Let's suppose you have some ice. This is ice. It's 1 kilogram. Okay. And you add, here comes my flames. You add some temperature. Whoa, that one was a crazy one. Okay. Flames. In other words, Q. Heat. Right? This is mass. 1 kilogram. The question is, let's say the temperature of this guy is at 0 degrees. This is 0 degrees Celsius. Okay? 0 degrees Celsius. The temperature will not increase. This is true, and we're going to do this experimentally. Okay, or you could do this experimentally right now if you want. If you take some ice and you measure its temperature, you'll recognize something very interesting happen when it hits 0 degrees Celsius. The temperature will not be increasing, so that thermometer will stay at 0 until all of the ice has turned to water. They'll both be at 0, yet a phase change happened. So what's happening? Well, basically the energy is coming in, and energy typically transmutes into kinetic energy. However, the electrostatic forces, the bonds, the electrostatic forces, the intermolecular forces, like hydrogen bonding or the London dispersion forces, these forces are holding it together. Okay, if I go back to this picture, this is a great picture of it. They're holding them together. The energy is pumping into these guys, and eventually it will go right into the bonds. The energy is going right into the bonds to break them up. Okay, when this happens, the overall kinetic energy isn't increasing, therefore temperature is not increasing. All the energy is going towards breaking the bonds. After those bonds are broken and they're farther apart like this, once again the energy that's being pumped in is moving these guys around like crazy. Okay, increasing the temperature. Then, when you hit your next critical point, so that it all depends on your substance. Okay, so for water, when you hit your next critical point, when these guys are going fast enough, when energy comes in, once again, instead of moving them around even faster, it will be intuitive for it to go after these electrostatic forces and split them apart even further. Okay, so now you even have a less dense substance and you visually see this as steam. Once all of the particles have transitioned, so once all their electrostatic forces have been broken, you'll then have an increase in temperature once again. Pictorially, what does this look like? I'm going to skip ahead for a second here, because I think it makes more sense if I skip ahead. Pictorially, it looks like this for water. Let's suppose you start with ice, negative 10 degrees Celsius. You have a hunk of ice. You raise the temperature. If you have a thermometer in a jar of ice, so suppose, actually I'm going to draw this. Let's suppose you have a jar of ice. And this theory, make sure you're paying attention to this, because this won't be spoon-fed to you when you do the question. You'll actually have to critically think about what's happening. So say you have some ice and here's some ice cubes. Whoa, not sure what happened to the last one. Okay, and you have a thermometer that's sitting there taking temperature. Okay, that's a thermometer. Here's what's happening. When this guy comes up to 0 degrees, temperature is increasing. Obviously, look at this graph. The temperature is going from negative 10 to 0 degrees. That makes sense. You're adding heat. Okay, so you're adding heat. Okay, whoa, that last flame is crazy. So once you hit 0, and you can calculate, here's the interesting thing, you actually can calculate how much heat you're adding just by using the specific heat capacity formula, right? MC delta T, that's standard. We took that in 4.4. So that's easy to do, but the thing is, once you hit this crazy critical point, I'm going to label that as the critical point, and that's fusion, right? Then you actually have to use a different formula to calculate Q, because this time there's no change in T, right? Change in T is meaningless. The energy is going towards the bonds, not towards the kinetic energy. So this is strange. By the way, it's not strictly just going toward the bonds. I'm just trying to make this a bit easier to visualize. But basically, this formula, Q equals mHF, it relies on the mass, but HF will be the heat of fusion, which would be a constant value for whatever substance you're in, kind of like specific heat capacity. Okay, that's your fusion formula. Then, once you pass melting, so now once all the particles have gone into the water phase, now temperature, the thermometer will read and increase again. So this is time, by the way. This is over time. And then once you hit the next critical point, so here's the next critical point, you get another phase change. Temperature will stay the same until all those particles have turned to gas. This is vaporization. Once you pass that, you're in business. Now you can go on forever, basically, until you go to plasma. Okay. So that's when temperature is increasing. When temperature decreases, the same thing happens. Okay, we'll get to these negatives in a second. But basically, when temperature decreases, your delta T will be negative. Therefore, you're going to force this to be negative as well to have some meaning. So that's basically it. I basically just told you exactly what needs to be done. And for some of you, you might be able to just shut this video off right now and get to work. But we'll just start with heat of fusion. Super easy formula to compute. It relies only on mass. So this only matters on the mass and the heat of fusion, which is the amount of energy, okay, joules, for 1 kilogram, right? Joules per kilogram. So hopefully that makes sense. You can reference these on our table. Here they are for certain materials. Heat of fusion right here, joules per kilogram for these materials. The heat of vaporization is off to the side. Okay, you'll need to reference these if they're not explicitly given. So, and by the way, let me go back to that for a second. By the way, what was I going to say? For this stuff, heat of fusion is the same for water and ice, but it's not the same for specific heat capacity. You have water, you have, ice here, and I think you even have steam. You have steam here. So keep that in mind, because you're going to be phase changing, and you're going to have to changing specific heat capacities. So that's where you can reference all these things. So when you do these questions, look at this question. How much heat is required to change 400 grams of silver from a solid to a liquid? Right? You don't even care about the temperature, because you just assume you're at the critical point of silver. I don't know when silver's melting point is, actually. You can look that up. 200 something maybe. Actually, no, way higher than that probably. But that's okay. Phase change is temperature independent, so you simply just need this formula. You have the mass in kilograms. You want this in kilograms. And then you reference silver's heat of fusion in the table, and you get that, and plug and play, and you get this. Simple. How much heat is required to change 410 gram, move that to kilogram, please, of water to, at 0 degrees Celsius is changed to ice at 0 degrees Celsius. So now a spectator looking at this is probably like, there's a mistake in the question, because how can you change from water to ice at 0 degrees Celsius? But now you know that it's actually temperature independent, and it's the same question as 1. Plug and play. Here is your formula. Plug in the mass. Reference for water or ice, it's the same thing, heat of fusion. That's why it's the same, because it's right on that critical point. And you get your answer. Round it to the correct number of sig figs, and you're done. So, moving on to vaporization, you can visualize that this will be the same thing. You just have to reference a different part of the formula, and you're at a different critical point. You'll be at the boiling point. Okay. How much heat is needed to change 60 gram of water? Move that to kilograms. At 100 degrees Celsius to steam at 100 degrees Celsius. Okay. Temperature, maybe I'll write this down. Temperature independent at phase changes. Therefore, you just need this. You just need the mass, heat of fusion, done. Right? Determine Q for steam changed into water. Hey, this is important. Let's do this question. Okay, looks like it's the same. Move that to kilograms, but notice how the direction changes. Direction changes. I'm assuming you've read these already, by the way. That's why I'm going some quickly here. Instead of going from a liquid to a gas, in other words, instead of going upwards in this direction, increasing temperature, you're going to go downwards. When you go downwards, you introduce a negative sign. And the reason you're going to do this is to stay consistent with change in temperature. That change in temperature is final minus initial, which means you're going to get a negative value for it. Therefore, to stay consistent with it, and to tell the reader what direction you're going, you have to place a negative in front of HF. You're going to have to independently know how to do this, okay, based on the wording of the question. So the opposite direction of vaporization, okay, you're condensing basically, will require a negative. Therefore, the reader knows, when I read this, I'll know that the energy direction is going down as opposed to up. Okay, this is critical. So now let's get to some multi-step questions. You can imagine that I'm not just gonna ask you for the heat of melting or vaporizing. I'm gonna ask you if you have a chunk of ice at negative 10 degrees Celsius, how much heat is required to get it up to 120 degrees Celsius. Okay, that's what I'm asking you. In which case, that's a 5-step procedure where you're going to have to add 5 individual Q values. Okay, so how do we know there's 5 steps to that? Well, basically, I would suggest drawing a picture for each one. I'm just going to erase this so you can kind of see the picture. Here you go. There's the picture. Both of these are very nice pictures that will be in a reference sheet for you. And if the question indicates to you that the temperature is increasing, you use this one. Whoa. If the question is indicating you that the temperature is decreasing, you use this one. So let's get to a question. At the 14-minute mark. Sorry this is so long. This question was a 2-step question. Calculate the quantity of heat required to 50 grams of ice at negative 10 into water at 0. So you're calculating, first of all, here's the first Q value you're calculating. That's Q equals MC delta T. And here's the second Q value you're calculating. Q equals MHF. Something I should note, it's written right here, that each line segment represents a step. If you have a plateau, which means a flat step, that's a phase change. So you use those formulas. So the formulas are written for you where you are at. Okay, so I think it's pretty self-explanatory. This is a longer question. Take a look at it. Hopefully it makes sense. You're going down this time, right? Okay, very beautiful picture I made for you here. Shows you everything. It shows you how a change in temperature is inherently negative when you're going down. Therefore, This needs to be inherently negative for the calculation at the end to make any sense. We are at the 15-minute mark, but let's do this one big question together. Okay, I can make a part 2 video, but I think you guys can bear with me here at the end. Calculate the heat required to change 10 grams of ice at negative 15 degrees Celsius to steam at 140 degrees Celsius. This will be 5 steps. How do I know this? Because I can visualize the picture. By the way, we're always going to be talking about water here, because water is the only substance I expect you to have the phase changes memorized at 0 and 100. You're starting at negative 15. This picture is extraordinarily small. Let's make it big. You're starting at negative 15. You're going to hit 0. You're going to hit 100. And you want to go to 140. Which means you're going 15 to 0. Plateau to phase change. All the way to 100. Plateau to phase change. All the way to 140. How many long segments is that? 1, 2, 3, 4, 5. You therefore can label this as Q equals MC delta T, that's Q1. Q equals MHV, that's fusion. Sorry, F, that's fusion. Again, you're going to use your specific heat capacity. Here's vaporization. And here is more specific heat capacity. So, the great thing is the mass is 0.0110 kilograms. You need to convert that. That's the common mistake. People forget to do that. And here's the key. The temperature change, delta T, will change. Delta T changes for each step because you're adding these up individually. So you please don't go 140 minus negative 15 to give you that 125 change in temperature. That's not correct because you're adding up individual sequences. So for step 1, you're going to have Q MC delta T. In this case, C is the same for everything. The specific heat capacity for ice, I believe, is 220 or 260 actually. It might be 260. 2060. Yeah, it's 2060. Joules per kilogram degrees Celsius times change in temperature. The change in temperature for the first step is going to be change in temperature is equal to 0 minus negative 15 because the final temperature is 0 right here and you're starting with negative 15 to give you a positive value. This means that cancels with this. Kilograms cancel with this. You're left in joules. You'll get an answer. Okay, 0.0 this times 2060 times 15 equals 309. Please don't round any of these steps. Not yet. Okay, I'll do step 2 over here. After step 2, I'll cut the video to the end so you can see the end result. I'll let you work on it. But step 2, you hit the this formula. Very simple step. Here's the mass. You reference HF for water. I don't have these memorized. For water, 3.34 times 10 to the 5. Joules per kilogram. It's great to write your units because you can see these canceling. So now again, you're left in joules. Everything should be in joules at the end. 3.34 to the 5. Gives you, again, don't round these values. You'll need to add up the individual steps at the end, so maybe I'll circle these. Okay, so hopefully you get the idea of this. Step 3, you're going to be using Q equals MC delta T. Perhaps I'll just highlight something here. Again, it's going to be 0.010 kilograms. Here, the specific heat capacity changes. And so does delta T. This time delta T is 100 degrees Celsius because if you're going from 0 to 100 degrees Celsius. So in this case, Q is equal to 0.010 times 4180 times 100. Okay. Whoa. Is that correct? Yes, it is because 100 times that. Very strange it came out. Did that be that? That's okay. I might as well just do them all. Next one is your phase change for steam. So notice how the mass never changes. So if you get this mass wrong at the start, you are getting every single step wrong. I think this is 2.26 times 10 to the 6, but let's take a look. 2.26, yes it is. This is your heat of vaporization. Joules per kilogram. Kilograms cancel. I'm just going to have enough space here. Sorry about this length of video. Talked a lot at the start. Tends to happen. However, hopefully it gave you some background to why you're doing this. Step 5 is your last Q equals MC delta T. So again, you have 0.0110 kilograms. Specific heat capacity is 220 now. And then your change in temperature, you're going to 140. So it's going to be 40 degrees Celsius because you're going 100 to that. So you have 0.0110 times 220 times 40 equals 808. Okay, joules. Now the final step is to add these things together. Okay, is to add all these things together. So if I was to just erase this top part here, your final step in green, so Q is going to be 309 plus 3340 plus 4180 plus 22600 plus 808 equals, holy smokes, 309 plus 3340 plus 4180 plus 22600 plus 808. And you know what, I'm fine with you just rounding. You can just round to lowest sig fig in question. That's fine with me. Okay, you can get some interesting ones, like in this one before here I kind of highlighted to you the true way of rounding these things, but don't really worry about it. You can just go to the lowest number of sig figs in the question, which in this case would be 2. I guess it would be 1, wouldn't it, here? 1 sig fig. Always a bit annoying. So in this case, let's just go to 2. Let's go to 2 here. Okay, in this case it's 3, 1. So make sure you're paying attention to that when I'm talking there. Maybe if I want you to go to 2, I'll explicitly write it. Okay, I should have wrote that mass to 2 sig figs. But if you want to go to 1, okay, if you wanted to go to 1, it would be this, obviously. Right, and that's fine. So that's it. That's a full question. That's the longest question you're going to do. I mean, as you can see, that question took 8 minutes. Sorry for the long video, but hopefully that gives you some background. Work on these practice problems. Then, of course, do the assignment. Then, of course, do the review. And then you can write the exam. So good luck.